Okay, so before, in the previous video, we spoke about energy, and specifically we're going to study kinetic energy and internal energy, and we're going to see how these relate to each other to eventually give us the conservation of energy. Okay, but now we're going to look at the first one, which is kinetic energy, and we know that kinetic energy is given by half mv squared, and it is literally energy associated with the motion of an object. Okay, so let's focus first on, well, in the previous video we saw that we had three types of collisions. We had an elastic collision, we had an inelastic collision, and we had a totally inelastic collision. And for an elastic collision, we saw that the relative speeds before and after collision were the same. For an inelastic collision, we saw that the relative speed after collision was less than before. And for a totally inelastic, we saw that the relative speed after collision was zero. Basically, after colliding, the two objects were moving together at the same velocity. Okay? But now let us focus first. We'll just have a look here on elastic collisions. And it says here, in an elastic collision, the sum of the kinetic energies of the objects before the collision is the same as the sum of the energies after the collision. Okay? So what we're saying here is that in an elastic collision, K initial equals K final. All right? So that means half mv, say object A1 squared, plus half mv object B, so this is B, that's A squared. These are both initial kinetic energies, is equal to half mv, so that's A2 squared, plus half mbv b2 squared. The point is the total kinetic energy, if you add up the kinetic energies of both objects before, they will be the same as the total kinetic energy after. But this is only true for an elastic collision. It's only true for an elastic collision. So the idea here is that we haven't lost any kinetic energy. Okay? So now, this is a very helpful little paragraph. For problems involving elastic collisions, we now have two tools. The momentum conservation law, which tells us that momentum of an isolated system doesn't change, and the fact that the relative speed of the colliding objects doesn't change. Okay, so what are we trying to say is that whenever you have two objects colliding, so I'm going to use this diagram now, when you have an elastic collision, you've got this object colliding with this object. What are our tools? Immediately, when you see, you have an elastic collision, what are your tools? First tool, conservation of momentum. Whenever we have two objects colliding and it's an isolated system, we have conservation of momentum. That is our first tool, momentum conservation. And the second tool, if we have an elastic collision, what's our second tool? Well, kinetic energy initial equals kinetic energy final. We know we have not lost any kinetic energy. And then a follow-up of this, maybe even our third tool, is that the delta V, no, I don't want to use delta V because it's not change in velocity, it's relative velocity. V12 final equals V12 initial, meaning the relative velocities after equals the relative velocity or relative speed before. Those are our tools for an elastic collision. Okay, so I think that's good for now. Maybe just have a look at this. I'm going to speak about this again later, but a totally inelastic collision, as you can see here, its velocity relative speed after collision is zero. Do you see that? So in this case, I'm not getting to that now, But in this case, we will lose kinetic energy. We had a certain kinetic energy before, and we will lose. Okay, but we'll get to inelastic later. But please understand what your tools are. Okay, cheers.